Hey guys, what's going on? My name is Nick, and I'm the creator of Frisbros. Frisbros is a top-down 2D couch co-op frisbee game that you can play with a friend. It's out now on Steam, and today what I want to do is I want to show you how I created the terrain movement system for the game. In Frisbros, I personally use this tile map system to make sand pits, quicksand, icy tiles, moving platforms, and a bunch of other terrains that I don't want to spoil for anyone who hasn't played the game. This video is going to be the first in a multi-part series to get the terrain system up and running. We're going to move pretty fast, so be sure to take your time with each step, and leave a comment down below if you have any questions. I'll be sure to do my best to answer them. Also, be sure to like and subscribe if you want to be notified the next time a video comes out. My next video is going to be focusing on creating some of the basic architecture for the system, as well as generating some of our first unique tiles. Now, if you've worked with Unity before and are familiar with the systems, I think that the most obvious solution to designing a terrain system would be to just place trigger colliders all over your world and make a massive switch statement in your character controller that reads the triggers and changes how the character moves. This is the solution I used for almost a year before realizing that there were too many movement types to handle in a single switch. If you're prototyping, the switch case is the quickest to code, but it comes with a lot of drawbacks. It bloats your character controller, it limits the system's movement to only the player, and you pay for the time you save coding, because now every time you lay down special tiles, you have to mold a trigger collider around them. In larger projects, this can take a ton of time, especially if you place your terrain systems in irregular shapes. Our goal with the system is to make it easy to create new tiles and to invert control of the data so that the tiles tell the player how to move instead of the other way around. As an added bonus, it would be good to make a reusable component that we can attach to any game object that we want to interact with the terrain system, such as exploding barrels or maybe immovable decorations, instead of just limiting it to the player. Now that we've defined our goal, let's set up our scene. For the rest of the video, we're going to set up our project structure, create a character that the player can move, and set up some basic tile maps. If you want to know more about setting up character controllers and tile maps, I've linked some resources down below, so you can deep dive into how these systems work. Let's start by getting some art. First, open up a new 2D Unity project, right-click on the assets, and create a new folder. Let's name this folder Sprites. This is where we will be storing all of our artwork. Next, in the video description, I've linked the 2 sprite packs that I'm using, and have created a consolidated zip that holds only the artwork that we want to work with. Go to the Google Drive link and click the download button. Then unzip the folders and drag the folders into the Sprites folder of the new project. The tile map and character that I'm using are 16 by 16 pixels per inch, so now we have to set all the artwork to that scale. Go to the characters folder, select all the sprites, and in the inspector, set the pixels per unit to 16. While we're here, let's also set the pivot to the bottom, the filter mode to point, no filter, and the compression to none, and click apply. If you're unfamiliar with these fields, what we just did is tell Unity that one world unit will be equal to the size of our character, and that their transform position will be set to their feet instead of the center of their body. Finally, we removed all of the filtering so that the pixels are crisp and highly detailed. Let's do the same for the single frame tile map tiles, except this time, let's keep the pivot at the center instead of setting it to the base. Tile sheet folder contains a single asset with all of the art, so in this case we want to set the sprite mode to multiple, pixels per unit to 16, filter mode to point, and compression to none. Then click on the sprite editor button. Let's use this window to slice this asset into separate tiles. First click Slice, set the type to Grid by Cell Size, and Pixel Size to 16 by 16, and give it a padding of 1 on the X and Y to account for the spaces between the tiles on the sheet. Then click Apply. The slicing process should take a while. Now that we have our art, let's prepare the game for working in top-down 2D. Go to Edit, Project Settings, and I like to dock the window that appears on the right. Then go to the graphics menu and under camera settings, set the transparency mode to custom axis and the transparency sort axis to y = 1. What this does is tell the camera that there are 2 sprites on the same layer overlapping each other, that it should decide which one appears on top by checking the transform positions and picking the one that's lower on the y-axis. Remember that we set the sort position of all our character sprites to their feet. So in the future, when our character walks in front of or behind objects in the scene, it will determine if they are above or below that object by checking their feet and seeing if they are higher or lower than the object itself. Now that our project is ready for top-down 2D, let's start working on the player. For the player, let's create an empty game object, name it player, and reset the player transform. Then in the inspector, let's click the Add Component button and pick a rigid body 2D. Set the body type to dynamic so that it can be affected by physics, and set the mass and linear drag to 1. These fields give the object weight and let it be affected by friction. Since this is a top-down 2D game, let's set the gravity scale to 0 so our player doesn't fall straight down. Then, set collision detection to continuous and interpolate to interpolate to make sure its physics detection is refreshed as often as possible. Finally, in the constraints check, freeze rotation Z to prevent the player from spinning around on its pivot. Next, let's right-click on our projects view, create a new folder, and call it Scripts. Inside of there, let's create a new script and call it Player. This is where we will define our basic movement while the terrain system is being built. But instead of opening it, let's just attach it to our player object for now and move on. Next, because it's good practice to separate an object's functionality into child objects, let's create an empty game object under player and name it Sprite Renderer. Let's give this object the Sprite Renderer component and give it a placeholder character sprite so we can see our player and set its sort point to pivot. Finally, let's also add an animator component to this object and move on for the time being. Now let's create another child object under player and name this one Collider. Then let's add a box collider 2D component to it and adjust it so that the box is just around the base of the player's feet. The values that work best for me are setting the offset to 0.1y and setting the size to 0.6 on the x and 0.2 on the y. What this will do is make a collider at the player's feet that prevents them from going through walls and still lets them sort the top half of their body above and below other objects in the scene. Now that we have our basic player, let's quickly animate them. Click on Window, Animation, and then open the Animator window. I like to dock this one in the center of my screen. Then click on Window again and go to Animation, Animator. Let's dock this one right below so that we can see both at once. With the Animator window open, go to Project and create a new folder under Assets. Let's call this one Animations. This is where we will store all of our animation controllers and animations. Open the folder, then right-click inside and go to Create Animation Controller and name this one Player_AC. Drag Player AC into the controller field of the Player Animator. Now you should see an entry and exit state in your animator. Right-click between them and select Create State Empty. Let's name this new state Idle, and it'll be our default animation for when the character isn't moving. Let's also right-click on the animator window again and create another empty state and call it Running. This is the animation that will play when the character moves. Finally, let's click on Parameters and click the plus icon on the right and select Bool. This will create a new condition that we can flip to go between the idle and running states. Let's call this one IsMoving and leave it false by default. Now right-click in the Project Animation folder and select Create Animation, and let's name this animation Idle after its intended state. In the inspector, set its loop time to true, then double-click on it and set its animation sample rate to 12. What this does is set the amount of animations we want to play per second. We are intentionally lowering it to match the speed of the sprite animations we have so it doesn't look sped up. Now that we have our animation, click on Project folder and drag the animation into the idle state. Finally, undock the animation window so you can see both the project and animation windows at once. Go to Sprites, Character folder, and drag all of the idle sprites into the animation frame. Now that we have our idle animation, let's press Ctrl D on the animation to duplicate it and rename this one Running. Then drag the running animation into the running state. Click on the player sprite renderer, and in the animation window select the running animation instead of idle, which is the default. For this animation, let's delete all the idle sprites and replace them with running animation sprites. We're almost done with animation. The last thing we have left to do is to right-click on the idle state and select Make Transition. Drag the line that appears to the running state, and in the inspector, deselect Has Exit Time, uncheck Fixed Duration, and set Transition Duration to 0. Then let's add a condition to the list and set IsMoving to true. The last step is to make another transition back from running to idle, but this time to set the IsMoving condition to false. Now that we have all of the character pieces, let's stitch them together with some of our own code. Let's go to the Project, Scripts folder, and open up the player script we wrote in our editor of choice. We're just going to make this script a simple character controller. It will let you set a default move speed in the inspector and move the character in 4 directions when you press the WASD keys. The script will also flip the character's animation to the left or right based on the direction they're walking, and switch between the idle and running animations based on when they're moving. Normally I don't recommend putting all this functionality in one script, but for the time being this will act as our placeholder until we have our terrain system up and running. In future videos we'll work on isolating the movement functionality to its own script. Let's go through the code to get a sense of what's going on. First, we're putting all of our code in a namespace to isolate it from other functionality that might be in our project. This prevents other code from interacting with our terrain system that we don't want getting interlaced. Next, we're using the require component attribute to enforce the rule that any object with a player script must also have a rigid body 2D attached. I highly recommend using this attribute if your scripts are expecting another component to be there. For the variables, we're creating a public float value that will be serialized into the inspector by Unity. This will be our player's move speed when it's unaffected by terrain. After that, we're creating a move velocity variable, which will capture the player's velocity, meaning the direction that the player is traveling. Then we have our rigid body, animator, and sprite renderer components that we created earlier. And finally, we have a boolean that will store information about whether the sprite is looking left or right, or in Unity terms, whether it's flipped. In the start method, we call the Unity function getComponent to collect the rigid body from the player object and the sprite renderer and animator from one of its child objects. In the update method, we call input.getAccessRaw and supply the strings horizontal and vertical to tell Unity we want to return a value of -1, 0, or 1 based on if the player is pressing the left button, nothing, or the right button. Then we do the same for the up and down buttons and capture this information as a vector too. The input raw value is then passed to 3 methods. Start movement velocity uses the value to calculate the movement velocity of the player by multiplying the direction by the speed the player wants to move. Set sprite renderer direction uses the input raw's x value to decide which way the character should face. If it's 0, that means we set the value to the previous sprite flipped value we collected. If it's -1, we set the sprite flip to be true because our character is facing right by default, and flip the sprite. If it's set to 1, we don't flip the sprite. Set animation state uses the input value to determine if it should play the idle or running animation by checking if the player is pressing any buttons. If they are, we flip the isMoving bool we created in our animator to true. If there is no movement, we flip it to false. The transitions we created earlier handle switching the animations between the 2 states. Finally, in the fixed update method, we use the rigid body's move position function to move the player. We do this by taking the player's current position and adding the move velocity we calculated for this frame times the fixed time delta between physics cycles. What this means is that every physics update cycle, Unity refreshes the player position and places them a little bit further into the direction they are traveling. We want to do this in fixed update because we eventually expect to flip seamlessly between transform and physics-based movement in our system. Now that we have our code, let's go back to the Unity editor and give it a try. Play the scene, and when you click play, your character should respond to your movement inputs. The last step we're going to cover today is Tilemaps. Before we start, let's dock the animation window down below since we will no longer be using it. If you're on the latest version of Unity, Tilemaps should already be built into the 2D project by default. To use them, in the grid hierarchy, let's right-click, then select 2D Object, Tilemap, Rectangular. This will create a grid object with a Tilemap subobject. If you haven't used Tilemaps before, this bundle of objects can be a bit confusing. The grid object itself is specifically confusing because although it does create a grid, the name makes people think that there should only be one, and that all tilemaps should be contained under it. This isn't exactly true. I prefer to think of the grid object as a room, which can be duplicated whenever there is a logical break between tilemaps. Thinking of it this way helps me modularize my levels and move chunks of them around. For now though, let's just focus on creating one. For the tilemap object, you can think of it as a layer to the room. To better visualize what I mean, let's rename tilemap to tilemaps below ground. After that, let's duplicate the object 3 more times and rename the new versions tilemap ground, tilemap over ground, and tilemap walls. Now that we have our structure, let's apply it to their sorting layers as well. Click on any of the tilemaps and click on Sorting Layer, Add Sorting Layers. In the window that opens, add the layers below ground, ground, over ground, and wall. Pay close attention to the way I spell these layers because we will need this exact spelling in future videos. Finally, let's make sure that they're ordered in ascending order, with default being at the bottom. Now let's apply the sorting layers we've created to their appropriate tile maps. The last thing we need is for our wall tile map to behave like a wall. Fortunately, Unity already has this solution for us. Click on the Tilemap Walls subobject and add the components Composite Collider 2D and Tilemap Collider 2D. You may have noticed that the composite colliders automatically add a rigid body to the game object. Let's set the body type to kinematic so it doesn't move and set the constraints to freeze rotation Z. Then in the Tilemap Collider 2D component, let's check the Used by Composite option. What we just did is tell the tile map to dynamically generate a collider around any tiles that you lay down on the wall's tile map layer. If the player or any other object runs into them, they will not be able to pass. Before we finish up, let's right-click on our project window and create a prefabs folder under Assets. Then let's drag our grid object into that folder to make a prefab of it so that it's easier to duplicate in the future. Now let's click on Window, 2D, Tile Palette. This is where we will make our tiles out of our sprites so that we can draw with them. Let's dock the tile palette on the right and click Create New Palette. In the dropdown, let's name the palette something like Basic Tile Set and click Create. In the project window, let's create a new folder under Assets and name it Palettes. We'll use this folder to store our tiles. Now let's go to the Sprites Single Frame Tilemap Tiles folder, highlight the entire collection, and drag it into our new palette. When it asks where we would like to save our tiles, select the palette folder and click OK. Next, go to the Tiles Sheet folder and drag the sliced roguelike sheet into the palette as well. Save the tiles to the same place and click OK. The roguelike pack may take several minutes to generate all of its tiles. Now that we have tiles in our palette, we can use them to draw. To test this, let's click on the ground tile map, then in the tile palette, click on the little rectangular button and select one of the dungeon ground tiles. Then let's click and drag it around the player to make some sort of ground. I encourage you to play around with the tile map and draw a little room for the player to move around in. Add some walls and some under tiles to see how the sorting works. When you're done, run the game and check out how it all looks. And with that, we've created the top-down 2D project for our system. I know it's been a lot of work, but consider it a crash course for all the tools that we'll be using to create our world. In my next video, we'll start designing and coding the basic architecture for this terrain system, as well as create some unique terrains that can either slow down or speed the player up in any direction. We'll also be adding ice tiles, which is a personal favorite of mine. So until next time, be sure to like and subscribe, and maybe check out my game Frizz Bros on Steam if you're interested in seeing all the crazy things that the terrain system can do once it's finished.